lecture series on MOSFETs, we talked of how to use an NMOS device as a linear amplifier. Okay. Now to have an NMOS operate as a linear amplifier, the transistor has to be biased in the saturation region. That is, the Q point should not be either close to the cutoff or close to the non-sat region, so that the output V out, the AC output, is the correct reproduction of the input, except that it is scaled by some constant K. Okay, so all the frequencies are intact. There are no harmonics that are going to be produced. So it has to be biased in saturation region. That implies that the ID, the total instantaneous current, drain to source current of the MOSFET device, is the saturation current. Okay, which means that you have the IV characteristics are given by the saturation, are given in the saturation region. VGS is the total instantaneous voltage at the gate of the transistor. Okay, and over here you see that at the gate you have an AC source VI, and you have a DC VGSQ over here. So now if you evaluate the output, okay, at which is VDS, so the output is VDS, we see that the output voltage it can be expressed in terms of the quantities VDD and RD as VDD minus IDRD. Okay, so there is a potential drop at this resistor. If you subtract this from VDD, you are left with VDS, which is the output voltage, right? Now, since VGS has both the DC and AC component, it turns out that this ID saturation current also has both the DC and AC components. So ID, the total instantaneous current, can be bifurcated into DC and AC components. Okay, and if you collect this in a bracket, you see the first part of the output voltage V0 is your DC part of the output voltage, and then you have the AC part, which is given by the lower case I and lower subscript T. So then you have the AC part as well. Okay, so they are both AC and DC parts. Now the output voltage is a combination of DC and AC values. So the time varying output signal is a time varying drain to source voltage. Okay. So you see VDS is this is the AC part of the signal, and if you recall last time we derived an important parameter, small signal parameter of the transistor, that is the transconductance gain. Now this transconductance gain is given by the gradient of ID by VDS curve. So in a sense, this is in the dimensions are as such as amps per volts, which means that your input signal is the voltage and the output is the current. Okay, this is your transconductance gain. Okay, and it's also in terms of the Q parameters, VGSQ, for example, and electrical conduction parameters of MOSFETs. So for example, over here, if you look at this expression, your GM multiplied by the gate source voltage, which is the input to the transistor at the gate. If you ignore the DC part of the gate source voltage, you only have the AC part. The output, the input is the voltage, the output is the current. Okay, so it's like the MOSFET as a linear amplifier behaves like an ideal AC current source in response to the input AC voltage. So the input is your AC voltage and the output is the current. Therefore, it's also called the transconductance amplifier, where GM is the transconductance gain. Okay, all right. So you can express this ID in terms of GM VGS. Okay, this negative sign simply shows that this output voltage VDS is 180 degree out of phase with respect to VGS. All right. So there is a phase inversion over here in VDS, between VDS and VGS. Okay. So now in order to have an AC equivalent circuit, you have to kill all the DC sources. So you don't need to consider VGSQ. Also, this VDD is a DC drain voltage which has to be grounded, which means what it means is that your node RD comes parallel to the output VDS, right? So in summary, the following relationships exist between the time varying signals for the circuit in figure 1. This is figure 1. Okay, and if you now what we are interested is in the time varying input and output voltages and currents. Only the AC quantity that we are going to consider over here. The equations given in the following equations are in terms of the instantaneous AC values as well as the phasors. So we have the VGS, this small VGS. So this is instantaneous. Okay, now this is small VGS. This VGS you can see is equal to VI. Okay, that's your the input AC voltage at the gate. Then if you consider the phasor representation of it, then this is capital or the uppercase letter V with a small subscript GS, which is the same as VI. Okay. Similarly, the output current is given as in terms of the transconductance gain GM as GM VGS. This expression comes over here. Okay. These are all small signal quantities or AC quantities. Similarly, the phasor term is there's a phase associated with these terms. Okay, then this is the same as ID equal to GM VGS with I and V capital, and VDS is the output voltage. Okay, output voltage which is minus ID RD, and I is the output current which is in terms of the input voltage for the transconductor amplifier GM VGS. Similarly, the same expression goes for the phases. So this is the DC equivalent circuit, and we can see that you can have an AC equivalent of that by replacing all the DC sources by ground. Okay, so all the DC sources are grounded. VGS, you don't see VGS over here. VDD is grounded, so RD is coming across the output, and the same relationships are holding that we have seen before for the time varying quantities and the phasors. Okay, for voltages and the currents, input and output voltages and currents. So the AC equivalent circuit is developed by setting the DC sources equal to 0. The small signal relationships are given in the above equations, and the node connecting the RD, so the node connecting RD and VDD is at the ground, is at the signal ground. Okay, so it becomes the AC signal ground over here. So you see, you are only left with the AC quantities. VI is your VGS, okay, which is given by the first equation. The same goes for the phasor relationship, and then ID is the output drain current, which in terms of transconductance parameters is GM VGS. Okay, so that's in amps. So that's the output, and that's the output current. So from the output current, you have the output voltage V naught, which is VDS, right, which is across the drain to source of the transistors. Okay, so that's your output. So the output is minus IDRD given the direction of the current, because the output signal and the input signal are 180 degree out of phase, so you have a negative sign over here. Okay. Okay. Now we have an AC equivalent circuit. You have AC equivalent circuit. Now all we need is a small signal circuit for the transistor. So we can plug this circuit, a small signal circuit, into the AC equivalent circuit to have a full-blown AC circuit for the analysis. So to derive the small signal circuit for the transistor, we assume that the signal frequency, we first assume that the signal frequency is sufficiently low so that any capacitance at the gate terminal can be neglected. Now you recall that the MOSFET has an oxide over here between the gate and the semiconductors. Okay, so there is an oxide. There is an oxide, and at the gate we have a metal or a poly silicon material which creates capacitance. Okay, so between the gate and between the substrate there's a capacitance. So in order to ignore the effect of this capacitance or to make the capacitor open circuit, we consider the signal applied at the gate source is of sufficiently low frequency, which simply open circuits the capacitance. Okay, or you can say the resistance due to the capacitive reactance is infinite. So the input to the gate thus appears as an open circuit or is of infinite resistance. Okay, now the small signal circuit for NMOS device is shown in figure 5. The phasor components are in parentheses. So now you have this VGS. Okay, this is the same VGS that's your input voltage applied at the gate. We are not considering any capacitance at the gate, so the input resistance is infinite. Okay, the input resistance is infinite. It doesn't draw any current, which means IG is 0. Okay, infinite resistance, infinite gate resistance, IG is 0. So you don't see any gate current component over here. Okay, now then you have this transconductance gain. Okay, so the output current ID is related to input as GM VI, which is the same as VGS. Okay, so we can write this as GM VGS. Given the direction of the current, you will have a negative sign for the output voltage. Okay, so this is GM VGS. So you as a linear amplifier in saturation region, the MOSFET device is behaving like like AC current source. Okay, so we have a dependent current source over here, which depends on the input voltage VGS. So this ID is GM VGS. Okay, so again it's a transconductance amplifier. So you have the input voltage and the output is the current. Okay, it's given by GM VGS. This is the gate terminal. Then you have the source terminal. Okay, and that's the drain terminal. This ID is flowing between drain to source, and the output is the VDS. Okay, so the only thing that is left is to consider the output resistance of the transistor, because the input resistance was assumed to be equal to infinite. Okay, so we did not consider any gate current into the circuit because the input resistance is very large. However, if you recall the characteristic of the transistor, in non-sat we have a linear or ohmic relationship with the current and voltage. But in the saturation region, in ideal MOSFET cases, the output resistance is also zero. Okay, this is I, this is B. You see the slope is zero. Okay, so you don't need to consider for ideal MOSFET, you don't need to consider the output resistance. But in actual MOSFET, this slope might not be. So this is VDS, which is V out. Okay. So what I'm saying is that in actual MOSFETs, this slope might not be flat. This could be something like this. Okay. So you might have a non-zero slope. And why this happens is because in ideal MOSFETs, your current is constant with respect to VDS. Your current does not depend on VDS. But what happens with VDS is that your channel width is being modulated by VDS, and there's a parameter called lambda. Okay, so we need to plug this parameter into the IV characteristics and find what is the inverse of this slope, which gives the output resistance. Okay, so let's do that. So you see the small signal equivalent circuit can also be expanded to take into account the finite output resistance of MOSFET bias in saturation region. Now in actual MOSFETs, due to the channel width modulation caused by VDS, there's a non-zero slope in ID versus VDS curve saturation. So you introduce this lambda, which is the modulation parameter. Now in ideal MOSFET, you don't consider this part, okay? And you only have this part, which shows that ID is independent of VDS. But VDS is an also horizontal electric field that is being applied between the drain and source, responsible for the flow of charges, okay, from source to drain. So, but what happens in actual MOSFETs is that your ID is not independent of VDS. So VDS also causes the channel conductance to change by changing its width. So the resistance of the channel is changing to VDS. So in order to find the output resistance, okay, here lambda is the channel length modulation parameter. Okay, if it is zero, then forget about VDS. That's the ideal MOSFET, but it's a positive quantity. Okay, in actual MOSFET. So the small signal output resistance, as previously defined, is given as such. So you have to take the inverse of this ID VDS. So this becomes ohms. Okay, and we do this at the constant VGS. VGS is the instantaneous gate source voltage. So VGSQ is where the transistor is biased. So if you recall this current relationship in over here, yeah, in the saturation region, if you take the differentiation with respect to ID VDS, just plug 1 plus lambda VDS over here, and you make this equal to VGS is your VGSQ. So this is your ideal drain current relationship in saturation. So if you take the derivative, you're left with lambda, and then the same term comes over here. And if you recall, this term was the DC current, in the MOSFET, drain to source current. So you remember what we did before was we considered the saturation current, then VGS has both the component VGSQ VI. Those were substituted, VI is VGS, and then you have three terms. Okay, the first term is the DC current, the second term is the AC due to this AC source, the third term is was neglected. Why? Because we assumed the small signal conditions, so VGS was much less than twice VGSQ VTN. So under these conditions, you don't need to. This term becomes insignificant. Another physical interpretation for the reason assuming of small signal conditions is that you're introducing harmonics with the third term. So you need to ignore this term. So in order to ignore this term, you have to make VGS as small as possible. Okay, and you note that this quantity is your GM, the transconductance gain. So GM versus VGS forms ID. Okay, so GM VGS product forms the small signal current ID. This is the AC part, and the first part is the DC part. So we can have this, write this as, we wrote this as IDQ. Okay, so you can see at the bottom we had the instantaneous drain current has two components, the DC component and the AC component. So let's bring this over here. The definition of the DC current IDQ, lambda is over here. So R0 is the output MOSFET resistance in terms of the channel width modulation parameter lambda. It's given a 1 over lambda IDQ. Now this small signal output resistance is also the function of Q point parameters, because your drain current, wherever it is, because you're considering it for a certain VGSQ. This is your VGSQ. Okay, I think it looks like a very flat, but it's not flat. It's something like this, right? And so this is your drain current. Okay, this is IDQ. This is IDQ. The expanded small signal circuit model of N-channel MOSFET is shown in figure 6. This is an expanded small signal model which includes the output resistance of the MOSFET. Okay, you have the current source, you have the input voltage VGS, the output is VDS. So note that this equivalent circuit is a transconductance amplifier, and that the input signal is your voltage at the gate. Input signal is the voltage, the output signal is the current. The output is the dependent current, and it's dependent on whatever you are applying the input. Okay, so you have to evaluate the current by using the transconductance gain GM. This equivalent circuit can now be inserted into the AC equivalent circuit of figure 4. So we have this AC equivalent circuit before. So let's plug this small signal model into this circuit of figure 4 to have a complete AC circuit. So this figure 7 is a small signal equivalent circuit of common source circuit with NMOS transistor model. So this is your transistor model, okay, with the output resistance. This is your transistor. Okay, so this part actually comes over here. This is your transistor. RD is your drain resistor. VDS is the output voltage. Okay. Now, as an example, this is from your course text. It says determine the small signal voltage gain MOSFET circuit or MOSFET circuit. Now, for the circuit in figure 1, assume the parameters are VGSQ as 2.12 volts. Okay, so let me bring this figure 1 over here. This is your figure 1. Okay, so VGSQ is given. Okay, the conduction parameter, you will see that you will have the conduction parameters. You will have the threshold voltages. Okay, you're given the drain current. So the drain resistance RD. So you have to find the small signal equivalent parameters. So this determine the small signal voltage gain of MOSFET circuit. For the circuit in figure 1, assume the parameter VGSQ as 2.12 volts, VDD is given as 5 volts, the drain resistance 2.5 kilos. The transistor parameters are given. Threshold voltage 1 volts, conduction parameter is 0.8 milliamp volt square. Then you have the channel modulation parameter in volts inverse. So this is volts inverse 0.02. Assume that the transistor is biased in saturation region. Now, the first thing is you need the quiescent current. Okay, why you need the quiescent current? Well, there are two reasons to that. First is that you need this in evaluation of GM, right? Directly, if you want to evaluate the transconductance gain, you have the conduction parameters. You can just plug these values, find the transconductance gain as we did last time. The other reason that you need IDQ is for the evaluation of the output resistance. Okay, you need it over here with lambda. So let's find this DC current value. This is Kn VGSQ. This is again the DC VGSQ. So this is 0.8. The conduction parameter is given as 0.8 over here, and you plug this value over here. Then you have this 2.12 is your VGSQ. 2.12. This comes over here. Threshold voltage is given as 1. So just plug these values over here, and you get the DC value of the current as 1 milliamps. Then from this DC, since we're doing the DC analysis, the output DC VDS, the output DC voltage VDSQ is given as VDD minus IDQ RD, okay, which is the DC part of the output voltage, which we have considered before over here. So this is the DC part of the output voltage. And if you're going to plug this in over here, yeah, You're going to bring this over here. VDD is 5 volts. IDQ is 1 milliamps, 2.5 kilos. It gives VDSQ as 2.5 volts. And if you have to check whether the transistor is indeed in the saturation region, then VDSQ of 2.5 volts is greater than VDSat, which is given by the overdrive voltage, VGS minus VTN. VGS is 2.12 volts and VTN is 1 volt. So if you substitute those values in this expression, you're left with 1.12 volts, and you can see that 2.5 is greater than 1.12 volts. So yes, indeed, the transistor, which means that the transistor is biased in the saturation region as initially assumed and as required for the linear amplifier. Now the transconductance gain, either you can evaluate from IDQ or from the definition of it. The direct definition is twice Kn VGSQ minus VTN. So just plug those values, you find that the transconductance gain in amps per volts is 1.79. Now this output resistance IDQ was 1 milliamps if you recall, and your lambda is given as 0.02. Okay, so lambda is given, this channel width modulation is given to you. So you have the output resistance of 50 kilo ohms, which is going to come over here. RD is 2.5 kilo ohms. We have evaluated for its GM. Okay, and you know what? Now you can evaluate the output voltage. So the output voltage is, you can see this is the current is minus GM VGS, and it flows in the parallel combination of R0 and RD. Okay, so if you evaluate the parallel combination of R0 RD 50 kilos and 2.5 kilos, multiply by 1.79, which happens to be the transconductance gain. That's your that's also the voltage gain. Okay, so because the ratio of V0 by VGS, so V0 over input voltage is your small signal voltage gain, is given at 4.26. Again, the negative sign is for phase inversion. So that's the voltage gain of a common source NMOS circuit. Okay, where we assume that the there is no gate current and the input capacitance of the MOSFET can be ignored for small signal conditions and low frequency of signal. So VI is a low frequency AC signal, so there is no gate current. Okay, and for this MOSFET, we consider the small signal, expanded small signal model, which includes the output resistance of the MOSFET. And the input resistance is infinite because we are not considering the capacitance. But we have a finite output resistance for actual MOSFET device with RD, which is connected as such in parallel to R0. Okay, because the DC is grounded. So the entire circuit is AC circuit. Okay, this is the AC is equivalent circuit of a common source NMOS device with a small signal. This is the small signal circuit of the MOSFET. Okay. Now the comment over here is that the magnitude of the AC voltage is about 4.26 times larger than the magnitude of the input voltage. So hence we have an amplifier. We do have an amplifier. It's a linear. Now note that the small signal voltage gain has a minus sign, okay, which means that the sinusoidal voltage is 180 degree out of phase with respect to the input sinusoidal signal. Okay, so this minus sign is, it means that in common source configuration, the output voltage is phase inverted. Okay, it's like minus 4.26, which is the gain multiplied by VI. So indeed, it's a linear amplifier. It's biased in saturation region. Okay, as we have seen over here, this is biased in saturation region, and the output you can see is 4.26 times the input voltage. So it's linear, but with phase inversion. That means your input output voltages are 180 degree out of phase.